What's up, everybody? Welcome back to Mathlete's Corner. In this video, we're going to continue looking into logarithms, but this is level 3. So the problems are in the difficulty of the final 5s in AMC 10s and AMC 12s. So hopefully it's a little less intuitive and straightforward. So let's get right into it. Our first problem is the 2014 AMC 12B problem 20. And it says, for how many positive integers x is log base 10 of x minus 40 plus log base 10 of 60 minus x less than 2? So the first thought when you see the inequality is let's condense the left-hand side. But we have to be a little more careful because these questions are meant to trick us and they want us to condense the left side. But what we're actually supposed to do is make sure we know what values of x are in the domain. Both of these terms here that we're adding have to be valid. So that means that x has to be in the domain of both of these terms. So x minus 40 has to be more than 0, and 60 minus x has to be more than 0. That means that x has to be between both 40 and 60. So now that we've got that done, and we know the domain of x, and we know what values aren't even in the domain, now we can try condensing the left-hand side. We get log base 10 of x minus 40 times 60 minus x is less than 2. Now, if we take 10 to the power of both sides of these, we get x minus 40 times 60 minus x is less than 100. Now we can simplify this out. We get negative x squared plus 100x. On the left side, we have a negative 2,400. When we bring the 100 to the left side, we get minus 2,500, and that's less than 0. Now, the left side is conveniently a perfect square, and it's negative x minus 50 whole squared, and that is less than 0. Now, since this part is a perfect square, we know that this is always true except when x is equal to 50. So that means for the original inequality to be satisfied, x cannot be equal to 50. Now we can go back to our domain. And since we know this, and we know that 50 is in the domain, we can just count how many numbers are in the domain, and then we can subtract 1 to get rid of 50. So we know the domain is positive integers from 41 to 59. So that's just 59 minus 40, which is 19. When we get rid of 1 to get rid of the 50 in the domain, we get our final answer of 18, which is option B. This gives us the insight that we always have to make sure that our solutions to any logarithmic equation or inequality, like in this problem, the solutions always have to be in the domain. So let's move on to the next question. So this is the 2017 AMC 12A problem 20, and it reads, how many ordered pairs A comma B such that A is a positive real number and B is an integer between 2 and 200 inclusive satisfy the equation. As we did in the previous problem, we have to make sure we know the domain for both of our variables here. And lucky for us, we're given the domains right here. So all we know is that A is positive, so A more than 0, and B is an integer between 2 and 200. So that means, this might be handy in the future, there's 199 possible values. Now we can focus on the equation. So the left side, we can keep it as is since it's not extremely obvious how we can simplify that. And the right-hand side, we can extract the exponent and it becomes 2017 times log base b of a. Now that we have this, we can think about the possible values of log base b of a. Now, we have to be careful about the possibility when it's equal to 0, but unless that's true, we can divide by log base b of a. Now, solving this new equation gives us two more cases. Log base b of a can be equal to plus or minus the 20/16th root of 2017. Now that we know the three possible values of log base b of a, we know that for every value of b, there are three possible values of a, and it's easy to check that all of those values will be positive, right? So if this is the exponent, since b is positive, a will also be positive. If this is the exponent, a will just be equal to 1. So that gives three solutions for every value of b. And now we can use that count that we had earlier, multiply it by 3 to get our final answer of 597, which is option E. So now we can move on to the next question. So this is the 2013 AMC 12B problem 22. And it says m and n are integers. They're both more than 1, so they're constants in this question. And we want the product of the solutions to this equation here to be the smallest possible integer value. And we want to find the sum of the constants m and n such that the product is that smallest possible integer. So in this question, we want to isolate x, but since x is inside a logarithm, we want to isolate log x. And you may think from the equation that log x is already isolated, but when I say isolate, I mean we want to separate it from the constants m and n. So say we have log base n of x, right? We want to convert that to log base x, or log x over log n. We want to convert that to log x over log n. So if we do that in this question, we get 8 over log n log m times log x whole squared minus 7 over log n plus 6 over log m times log of x. And then we have that constant term at the end, minus 2013, and we know that that is all equal to 0. Well, now that we have this equation, we notice that here we have log x squared, here we have just log x, and here we have a constant. What does that remind us of? Well, it's just a quadratic, except instead of the variable being x, the variable is log x. So now we can go back to the question, and we see that the question is focused around the product of the solutions. And now it makes sense, right? The product of the solutions, sum of the solutions, that's Vieta's formula. But if we want the product of the solutions for x, how do we work with the log x? How do we get rid of that? And the answer to that is we don't need to get rid of it. Because as we know, if we want to take the product of the values of x1 and x2, right? Say x1 and x2 are the two solutions, and that's the product. If we take the log of that, right, that's just equal to log x1 plus log x2. So instead of finding the product of the solutions for x, we can find the sum of the solutions for log x. And now we know where to go with this. We can just plug in our coefficients into Vieta's formula. So we have 7 over log n plus 6 over log m over 8 over log n log m. And now when we simplify this, it just comes out to 7 log m plus 6 log n over 8. And this still looks pretty messy, but we know how to condense logarithms. And since we know that, we can turn 7 log m into log m to the power of 7. And we can turn 6 log n into log n to the power of 6. So essentially, this all just comes down to log of the 8th root of m to the 7 n to the 6th. And we want to minimize this. So when will this be minimized? When the value inside the log is minimized. So let's just isolate that. And now we have something a little more cleaner that we can work with. Now let's go back to the question. And we want the value of m plus n. So at this point, we should start trying to do a little bit of bash, but not just random bash, plugging in random numbers for m, more a coordinated approach for calculating the values of m and n. So if we go back to our expression here, we know that this has to be an 8th power, which means it has to be a perfect square. And since m to the 6th, n to the 6th is a perfect square, m has to be a perfect square. Because if we have two perfect squares, then their quotient, if it's an integer, it has to be a perfect square. Since we know m is an integer, m has to be a perfect square. So now we can start testing values of m that are perfect squares. And obviously we know that m is more than 1 because of the problem statement. So we can set m equal to 4 and work from there. So if we have m equal to 4, we're looking for the 8th root of 4 to the 7 times n to the 6. After testing out some smaller values of n and working our way up, we find that n equals 8 is a possible solution, and that's because it comes out to 2 to the 14 times 2 to the 18, and this is 2 to the 32, which is 2 to the power of 4. So since that works out, we have m equals 4, n equals 8, and obviously we don't know for sure that that's the smallest possible value, but we can use the fact that we have multiple choice, right? So if m is 4, n is 8, 4 plus 8 is 12, and that just so happens to be our smallest possible option. So the main idea in this problem was to just isolate that log x as a starter and then convert it into a quadratic in log x, and then identify that the product of the solutions of x is equivalent to the sum of the solutions for log x. That's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button, and we'll see you next time here at Mathlete's Corner.